this is where we got to, right? We were like, okay, the normal distribution, it's cool, it's useful, but up until the end of yesterday, we'd never really thought about what's the probability density function of the normal distribution. We'd looked at numbers. We were like, what's your mean? What's your standard deviation? We just looked at the concrete details. We called them empirical data, right? But then at the very end, we introduced these guys, and we kind of promptly felt ill because it just looks terrible, right? Now, the particular point at which I left you on a cliffhanger was when you start with a probability density function, you're going to go to work out probabilities or variance or anything you like. You're going to go there by integrating, right? So the cumulative distribution function is what you get when you integrate this guy. You remember that, right? Now, the only problem is, and I'm not going to write it up again, but the only problem is when you get to try and think about this guy, you run into some trouble, right? And you're like, was it really necessary to print that out? And the answer is yes, it absolutely was necessary, because we have to justify why from here we're going to go in one of 3 different directions. And you need to have these directions down because they're going to chart the path for us to the end of the term, which is like a whole 48 hours away, but anyway, okay? We've got one of 3 options to choose to deal with this particular problem, right? I do not want to integrate this thing. I'll do anything I can to avoid this, even though it's like technically possible. So we've got 3 alternatives, and very conveniently, I promise, I didn't plan this. It's just the way it is. We've got 3 ways to deal with this, and they all start with the letter t. So this integral that you get, and this mess out of it, the first thing is you can just hand it off to technology. You can just say, okay, I've got software. I've got Desmos, GeoGebra, Wolfram Alpha, whatever you want, right? Even though we don't want to do this by hand, computers can, all right? That's something we can deal with using that kind of software if we have it, right? But often you don't have access to that kind, like you don't get to bring your laptop in with you during a test or something like that, right? So that leads to these other 2 methods that start with T. Today's one that we're going to handle is the trapezoidal rule, because if you think back to integral calculus, the whole point of talking about trapezoidal rule at the end of that topic was to say sometimes you get an integral and you're like, I don't know what to do with it, but I can still approximate a value by thinking about areas under curves. You can find areas using whatever shape you like, right? And then tomorrow we're going to go look at 1/3 last way, which is a table of values. We call it a statistical table, which kind of basically is this, right? You take the numbers that technology has arrived at, and then you like print them out. Here are the numbers, and then use them, interpret them as appropriate. Okay. So as promised, this is the one we're going to focus on today. And what we're going to do is I'm going to try and hit 2 birds with 1 stone. Okay. Number one, I'm going to show you how this works with this particular probability density function. But secondly, I want to try and get at this weird chestnut which we've sort of been assuming, and I really hate when we assume like something is true and don't give you any reasons why. You know when you start from the mean in a normal distribution, and then you go out 1 standard deviation. Here's the mean, and then we go out in the highest part of the bell curve, right? We say that there's a certain percentage of people that we expect to be within 1 standard deviation. Does anyone remember what it is? It's 68. Very good. It's 68%, right? That's within 1 standard deviation. You go again, go 1 more step, you go further out from the middle of the bell curve. Does anyone remember the next number? 95. It's 95. Okay, we get to the 7 when we go a 3rd standard deviation away. It's quite odd. That's 99.7. Now, we handed you these numbers and we were like, they just are, okay? Like we came down from Mount Sinai and we're like, here they are written on tablets of stone, but we had no idea why they were the case. We're going to unpack where these numbers come from by means of this, okay? We're only going to do one of them because once we do one of them, I think the first one is the easiest one. The rest of them sort of follow in the same way. You can use exactly the same techniques, but we might as well just try the easiest one, which is the first one, okay? So, little subheading, which is trapezoidal rule with the normal distribution. And obviously, to use the trapezoidal rule, we need to remember, what is the trapezoidal rule again? Like it was a whole topic and a half ago. If you have your reference sheets there, you can use it, okay? Well, let's see if we can do this, okay? Firstly, remember, it's a way of approximating areas under curves, right? So if you have an integral right? If you have some kind of integral, I would normally write f of x dx, but I do notice that I don't like the f of x version of this normal distribution. If I can, I'm going to use this f of z version because it's just a teeny bit nicer, okay? So instead of writing f of x dx, I'm going to write f of z dz, okay? It's just a different pronumeral. It's fine, it still works the same way. We're going to approximate, so there come my wiggly equal signs. And then we think about how you do the area of a trapezium. So what I'm going to do is I'm just going to write over here. You don't have to write this down, but maybe it will help for you. This is just the area of a single trapezium. That's just one trapezium. When we say height, we mean like the perpendicular height. What are A and B? They're the two parallel sides, right? So we would say this is for one trapezium. How do we bring that in over here? Now I'm actually going to take this same H thing that comes out the front, right? I've got to work out the heights of all of my trapeziums that I'm going to use. And then comes in, well, a bit of a mess, right? These parallel sides, if you have a think about, if I gave you some random function like this, the parallel sides all run vertically. Do you remember that, right? And so you're like, oh, here's a trapezium, there's a trapezium. You get the idea, okay? So because they're all vertical, I get them from function values. Does this ring a bell at all? So we would normally write something like f of a. That's your first function value. You're also going to have f of b. That's your last function value. And then all your ones in the middle, you see all these ones like say, here's another color. Say this guy right here. Here's a function value right here. It gets used twice, one by the trapezium on the left and one by the trapezium on the right. Do you remember that? Okay, does this ring a bell? It's on the reference sheet. So what I do is, for every other function value, I double it, okay? There's the first one, there's the last one, and all the rest, I have to do them twice. So how would I write this? I would normally say something like, well, just take your first function value, z's, take your second one, and just keep going. Like however many middle values you've got, just put them all in there, and then you're done, okay? Now this guy more or less is on the reference sheet. So here are all your function values here. You got your first one, you got your last one, you got your middle ones, and I just have one more question. How do we work out this H business that's right out the front? How do we work out the heights of each of the trapeziums? Do you want to have a go, Ray?
The difference between B and A?
Okay, so I am definitely going to use the difference between, let's call that A and that B. So this is the distance here. The difference between B and A, I find that distance by subtracting. Do you agree with that? B minus A. But when you have a look here, I just made this up, right? How many trapeziums do I have? I've got like 1, 2, 3, 4, 5 in this case, right? So if I have 5 trapeziums, B minus A is not the height of each trapezium. It'd be B minus A divided by
2.
Well, in this case, by 5, because I have 5 trapeziums, right? If I had 3 trapeziums, I'd divide by 3. If I had a million trapeziums, you get the idea, right? So we generalize this by saying n, where n is the number of trapeziums. So I'm going to write in here, this is B minus A over n. Okay. Do you remember, I hope this is ringing some bells. Our task now is to use this on this guy, and we wanted to verify this particular result. Maybe we should write that down. Okay, what are we trying to do? We're trying to confirm or verify that 68% of a population is, how would we say this? Within one standard deviation of the mean. Within one standard deviation of the mean. And I'm just going to write mu there because I think we've written this enough that we get the sense that that's why we use that Greek letter. Okay, so what would be the integral that should, if we get it right, give us 68%? I'm going to need to start somewhere and end somewhere. So where do I start if I'm within one standard deviation of the mean? Okay, so let's draw ourselves a little little normal distribution here, right?
-1 to 1.
Ah, okay, well done, Saray. So right in the middle there is 0. There's our z-score. -1 is off to the left, one standard deviation, and then +1 is to the right. Is that okay? So this is going to be my boundaries, -1 to 1. And then I've got this as my function, so I'm going to write that gross 1 on root 2 pi e to the -1/2 z squared dz. This is what I'm after, okay? Now what I want to do here is I want to look at this before I just rush to start like putting numbers in. I want to see if I can do this any better. For example, if you have a look at this shape here, the normal distribution. When we were trying to come up with this shape, we said like what characteristics does it have? It's like asymptotic, but I wanted you to remember it's symmetrical. You remember that? Like that's the whole point of it. So when areas are symmetrical, we can sort of take advantage of that fact to make our integrals kind of nicer. Do you remember that? Think about this. This is the area I'm after here, from -1 to 1. How can I take advantage of symmetry to come up with a nicer integral instead of this one? Have a look at the shape, right?
You go 0 to 1 and
Yeah, can't I do this in half? If I do half, and I love 0 because of how easy it is to evaluate stuff, right? So if I go from 0 to 1, like why go to -1 because it's negatives, right? That's gross. If I go from 0 to 1, if I find that and then just double it, that should be the same. Do you agree with that? So I'm gonna write that down. This is equal to 2 lots of the same integral but from 0 to 1 instead of -1 to 1. And then here's all this other stuff in here. Okay. At this point, I'm like, okay, this is better, right? I'm going from 0 to 1 instead of -1 to 1. I think I can go better again because see this, like this came from the weirdness of the normal distribution, right? But it's just a number. Like 2 is a number, root 2 is a number, pi is a number. I can factorize all these out, right? And then I don't have to deal with so much inside the integral. So let's go ahead and do that as well. It's a fraction, so it's going to go over root 2 pi. So far, so good. And then the rest of it goes as before. Okay, is this better? Because remember what I'm going to have to do, right? At some point eventually, and we're almost there, I'm going to have to put lots of different numbers into here, right? I'm going to have to do all of this function here, function there. Like, I don't want to have to put in this every time I go to the calculator. So the less I have to put in repeatedly, the faster it's going to be for me. Okay, one last step. The trapezoidal rule, right? I need some level of accuracy. Like here I was like, ooh, 5 trapeziums, or maybe 2, or maybe 3, right? I'm going to suggest that what we pick, it's a sort of a nice common number, is we go with 4 trapeziums. So if I suggest that we use 4 trapeziums, you might also hear this as 4 intervals, right? Or you might also hear it as 4 applications of the trapezoidal rule. They all mean the same thing.
5 function values.
Sarang's on the ball, okay? So if I've got 4 trapeziums, right? In fact, I'm just going to draw 4 trapeziums myself here, right? If it was like this, there's another one, there's another one. That'll do. There you go, 4 trapeziums. And you can literally count up the number of vertical lines, right? 1, 2, 3, 4, 5. So 4 trapeziums means I'm going to have to put in 5 numbers up here, 5 function values. So I've got to find out what they are. Now, you get those function values from your boundaries, right? So I know I'm going to start at 0, and I'm going to end at 1. So I need 3 numbers in the middle. How am I going to get those? I think.
Split it up.
I'm going to split it up. Sophie, what are you thinking? What numbers are we going to use?
Would you not just divide it by 3?
Yeah, now I'm going to divide, but what am I dividing by again? I'm just going to point it out up here, right? I'm dividing by however many number of trapeziums I got. I have 4, okay? So this distance here is 1, so therefore I'm going to go a quarter every time. Are you okay with that? I'm just going to go ahead and write these as decimals because we're not going to be able to avoid decimals for very long. So 0.25, 0.5, 0.75, okay? Are you good with that? Do you see I've got these values that are going to go in here, okay? Just one last thing before we actually I told you to get your calculators out. Before we start crunching numbers, you know how we changed the boundaries from -1 to 1? We changed it to 0 to 1. Remember that? It's nice because 0 is easy to evaluate. There's one other good advantage that comes from this, which is that because we're approximating over a smaller interval, we get more accuracy. Does that make sense? I kind of get 8 trapeziums for the price of 4. Does that make sense? Think about it, right? Here's the area that I've got, right? If I did the whole area with 4 trapeziums, then it would look something like this.
Why don't we do an 8 then?
Do you agree with that? Like that's what I would get, okay? But because I'm just focusing on this orange part, right? I'm like, oh, I have extra trapeziums just in this little area here. So more trapeziums equals more accuracy, okay? Now to the question of why don't I just do 8 in the first place, you're like, I'd rather do less rather than more. If I can do less and still get better accuracy, then let's go for it, okay? So what I'm going to now ask you to do is draw up for yourself a table of values. It's going to look something like this. It's got to be wide enough because you're going to have to fit in 5 of these numbers in here. So your top thing is going to be a value of z. And then what you're going to put inside, what you're going to evaluate here, is whatever the integrand is, right? In this case, it's e to the negative a half z squared. Be super careful with your calculator. And then for each value of z, you're going to put in those numbers. So I think we said 0, 0.25, 0.5, and so on. We better be ending at 1. This is a bit of crunch work, so I'm going to give you some time to go ahead and do that. Fill these in. Can you give me 3 decimal places? I think that should do it. 3 decimal places. And what I'd love to see you on your page have is this table with the right numbers in there, and then we will put them all together into this formula. Okay, off you go. What have we done so far? We looked at this integral, right? Before we leapt to the trapezoidal rule, we did a couple of things to simplify it. We used the symmetry. We got rid of this coefficient out the front, so things are looking good. And then we started evaluating. We started crunching numbers, right? So now what we can say is, this integral, the one we started with, I'm now going to use the trapezoidal, which means I'm now approximate. You see that? Okay, so I'm no longer equal to that. I'm now approximately equals. The 2 on square root 2 pi. It was at the front of the integral. It had nothing to do with us crunching these numbers. You never had to type in 2 on root 2 pi, all that kind of thing, right? So that guy sits out the front happily, okay? Don't forget it. It's an easy thing. Like, we made it nice and neat to get rid of it, but you've got to bring it back, okay? And then in here, wow, this looks like a lot, but this is just the trapezoidal rule. Do you see what my h on 2 is? H on 2, there's my 0.25 on 2 as an added bonus, and this is slightly coincidental, but that 2 out the front cancels with that 2 that we have down the bottom, so like, yay, less stuff I have to do. And then here come my function values, first one, last one, and then I double all of the middle ones, okay? Now you guys have already popped those values down in your table of values, so I'm going to put them onto this line here. Right? What have I got here? 0.25 on square root 2 pi. Here come the numbers. So, first one, predictably, is 1, because we put in e to the power of all of the stuff times 0. So you're like, cool, that's easy. I then skip over all the way to the end, right? 0.607. There's the first and the last one, okay? And then I double all the ones in the middle. So let's go ahead and get those down. I've got 0.969, 0.882, and then 0.755. By the way, one of the great things about having this table of values so logically set out is that when you have a look at the numbers, you kind of know what you're evaluating. You're evaluating the normal distribution, right? Well, we're evaluating a scaled version of it, okay? So you can see it sort of coming down gently. Question?
Should we use decimals or fractions?
So,
Because it's an approximation, we could get away with it.
yeah, okay, so this is a good question. Should we use decimals or fractions? In a sense, the short answer is it doesn't matter, because we're going to get a number out here in the end. You can see I've gone to decimals because I knew from the function I was dealing with, I'm like, gross, there's not going to be nice, neat fractions that come out of this. So I'm like, forget it. The advantage of fractions is you get precision. Like, I can say, 4/7, which is exact, rather than some, I don't know, it's like 542, blah, 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 blah. I'm like, I will get some recurring decimal here, and I have to cut it off somewhere. So I'm like, ooh, exact. Not exact, right? But here, like, there's no way you were going to write the fraction that, like, it would just be a waste of space, really. So that's why you can see I've got decimals here. I should close my big square bracket. I have been a bit messy out the front because I've got a decimal on a fraction, but I'll tidy that up shortly. Okay? Do your numbers look okay? Has anyone already put it into their calculator?
Oh,
Okay, give me all the decimals you get. 0.
0.68009685.
Thank you. I'll treat that as okay, right? So we've got a number out here, right? 0.68. What did we set out to try and do? The answer was we were trying to verify that 68% of the population is within a standard deviation. And 0.68 as a decimal is also known as 68% as a percentage, right? So now you know these 68, 95, 99.7, they didn't come out of thin air. They came from here. Does that make sense? Okay. Question. Check your calculator. It is, I will say, like, with all these approximate methods, the danger is it's so easy to screw up something in your calculator.